Good morning. This is Lloyd Jester Barber. And by the way, this is the continuation of Ralia's report on Sustainable Future System. Sustainable water and wastewater systems. Water is often envisioned as bloodstream of the biosphere. It is a universal medium that is crucial for sustainability of both ecological and human societies. Although sustaining life is one of the main key purposes of the water, present-day agriculture and many industry branches heavily rely on the abundance of the water resource. To plan sustainable utilization of water resources, we must understand how the water cycles. A water cycle works at the global and local scales. The amount of water on air is finite, and the natural water cycle is a system that controls the circulation and redistribution of that resource. Annual evaporation from the ocean is about 80,000 cubic miles versus 15,000 cubic miles from the land. Given the amount of water evaporated and precipitated are not almost equal, the total amount of water exchanged between the atmosphere and the Earth's surface is about 95,000 cubic. Here are the examples of possible actions that help to keep combined water systems sustainable. First, the water regime management. It keeps the aquifer levels within appropriate range, prevent flood damage in developed areas, and prevent excessive erosion. Water quality. Minimize the export of pollutants to surface water or groundwater. It minimizes waterborne sediment loading, and also minimize pollution from sewage, protect existing vegetation. Next is the water conservation. Control water extraction and use. Promote the use of rainwater and stormwater, where such use does not adversely affect existing environmental values. Promote the reuse of wastewater effluent. Reduce irrigation requirements. Promote opportunities for localized supply. Water value. Enhance water-related environmental values. Enhance water-related recreational and cultural values. Add value while minimizing development costs. Next is water conservation and protection technologies. Although residential water consumption accounts for a smaller fraction of the whole, domestic water economy is considered an important factor in urban sustainability. The overall domestic water use is expected to grow as world population grows, di ba? So, mo ni siya ang mga different places or mga factories, basta ano siya guys, so kung saan nyo makita andara sa pictures. Okay, typical US home water use accounting. Mo ni siya ang example sa actually sa US na siya, this is Philippines. So tanan sila doon ay showers, so it takes 19.5%, and what washers 22.1%, toilets 18%, dishwashers 1.5%, baths 2.7%, leaks, so expected na ginaning leaks, no, 8.8%, faucets 23.9%, and other mga iba na mga usage is 3.4%. So muna siya ang mga typical sa US home water. Okay, next slide. Water conservation strategies. So as the population grows rather, so does the stress on available water resources. Hence, there are numbers of water conservation strategies. Limiting the consumption. So application of policies, economics, and technologies help regulate the demand. Um, Policies may include restrictions and bans on certain types of water use, standards for fixtures and appliances, enforcement or recycling, and etc. Economic measures, such as setting prices of water consumption, typically make people more diligent about their water-related activities. So, basta na gani money involved gani, ano ganang tao. So, technological advances may help us use less water for the same function, or it could be water economy washers, toilets, etc. So, reuse and recycle. Designing systems for reuse and recirculation of water in both domestic and industrial applications are involved in this approach. For example, treated wastewater can be used for irrigation, or water can be recycled in certain types of car wash system. Diba? Elimination of losses, regulation, metering, water-sensitive design, and smart technology are key factors contributing to this strategy. Leak identification systems, smart controllers for water use are some of such conservation technologies. Next is the pollution prevention. Less pollution creates more opportunity for water to reuse and conserves natural water reserves. Regulatory policies are introduced on water discharging facilities. Also, numerous technologies exist to treat the effluents from domestic and industrial facilities. Water treatment systems. Water treatment technologies are designed to eliminate harmful effects of pollutant and natural substances to human health and environment. These technologies are often placed at the transitions between the environment and human sphere to adapt the water quality. So, mo ni siya, water treatment system, di ba? Makita natin yung tanan sa YouTube, kung nasa lagi butang nga mga something, you know. And then, nagtinaw ang tubig, mo na to siya. Sewage water before and after treatment. Mo na siya, guys. Centralized water treatment. Mao ni siya ang approach implies treating large amount of water at large rates in a central or location and distributing that water via networks of pipelines, channels, and intermediate reservoirs. So water district. Mao siya water district. Ano siya? And engineered ecological systems for water treatment. Traditional water treatment plants accomplish an important function. However, these facilities themselves produce significant environmental impact by consuming energy, producing emissions, byproducts, and waste to be disposed of. Wala na ng end. Pindot na, sorry. One of the trends in improving the environmental profile of wastewater treatment facilities is the design of ecological systems that mimic natural processes of neutralizing the pollution. So, ecological system could mimic the natural processes of neutralizing the pollution. So, mo siya ang ecological system. So, decentralized systems for water treatment. Decentralized system of water purification frequently become technologies of choice in developing countries because they do not require huge infrastructure or can be set up by quicker when infrastructure is destroyed. Diba? Ano siya? Applied renewable energy technologies. Renewable energy has been a catchphrase of recent decades. It has been both the subject of government policies and extensive research. We are searching for efficient ways to move from the easily accessible but finite fossil fuel energy to other types of energy available on Earth that are either unlimited or can be replenished within a much shorter time scale. The term Renewable essentially means that the energy source is not exhaustible on a human timescale. This, however, does not always mean that it has infinite capacity or con- constancy. We will see that different sources of renewable energy have different limitations, which must be taken into account when tuning the technologies to a particular application and locale. The main types of renewable energy resources are schematically summarized below. So these are the mga types ng avatar siya. Solar, wind, geo, hydro, bio, and tide.
Role of energy technologies in sustainability. Since energy is the main commodity ensuring well-being and sustainability of human society, the role of energy technologies is critical. Efficiency with which we can convert and distribute energy essentially determines our standard of living. Speaking the system's language, sustainability would require maintaining the stock of usable energy at the demand level. To make sure the society demand is met, the energy supply rate of the left-hand valve should match the energy utilization rate of the right-hand valve. It is it is the supply valve where energy conversion technologies play the major role. What can be done to maximize the energy conversion rate at the supply valve? First, maximize efficiency. This depends on the stage of the technology development, physics of the process, materials, design, and other things that may be improved through research and development efforts. Second, scale up the conversion system. Feasibility of the measure may be limited by technology cost and available space or land area to accommodate the equipment and etc. Tune technology to local source and conditions. Local conditions will dictate the adequate choice of technology to employ. Obviously, the solar energy is great where there is a lot of sun, and wind energy options would be suitable to the places where are windy. Also, system design should be adapted to the geometry and timing of the natural resource, such as supplemental technologies as tracking and energy storage will help increase the overall conversion. Building integrated solar energy technologies. PV basics. Since this report is already discussed by the previous reporter, so this is just the review. Okay, so PV basics. Photovoltaic PV technology is one of the way to convert solar's resource into usable energy, specifically sunlight to electricity. Photovoltaic conversion is enabled by certain semiconductor materials, which have a property to generate electric current when they absorb incident photons. Absorption of light, generation of charge carries electrons and holes, separation of charge carries so that they can perform work. So from solar cell to solar module and solar systems. This effect is physically realized in the certain semiconductor materials example, the monocrystalline silicon, the amorphous silicon, and the polycrystalline silicon and cadmium telluride. So PV application in buildings. Current applications of solar photovoltaics are adapted to the following scales. Portable, small electronics, example calculators and computers, and etc. Distribution power generations, the home's isolated equipment. Utility scale power to solar farms. In the scale-up process, the single PV cells are combined to modules, and modules can be arranged into arrays, cells, modules, and arrays. The Building Integrated Photovoltaic, or the BIPV, are multifunctional materials that are both structure supporting and power generating at the same time. Building facade with integrated photovoltaic panels. Well, the main function of a conventional PV system is efficient power generation. The building integrated PV systems, which become the components of the building envelope, must satisfy a number of additional requirements such as appearance, color, image and size, the weather and tightness, wind loading, durability, maintenance, safety during construction and in use, fire electrical structure, stability, and also the cost. So in this table we have the advantages and the challenges. First advantage is a lower cost to multifunctional nature of the material and due to more efficient design. The currently PV contributes 0.5% to national energy demand. The DOE expects to reach the 50% with BIPV implemented. Second, improve aesthetics. Panels are produced as facade lining, roof tiles, slates, shingles, windows, glazing, etc. Thin film PV can be applied directly to conventional building materials because the flexible and light. Also, challenges would be systems orientation, weatherability, durability are the factors that affect the system's performance. Those parameters may be not easy to optimize if it is BIPV rather than add-on PV. BIPV modules can be heavier than regular building elements because of potential overload. New building standards and codes need to be in places to regulate this integration. BIPV modules are costly compared to regular add-on PV due to their multifunctional value, but that is not always recognized. BIPV is not mass-produced, but rather custom-made, and that adds to the price. Social acceptance. Not many see long-term value because PV technology is thought to be soon outdated. There should be more acceptance from contractor and end users alike. There are following PV integration options. First, the shading systems and the rain screen systems. The shading systems, this includes louvers, either horizontal or vertical, which may be mounted outside the building or over windows or balconies. Their function is to shade the windows from excessive light. So the rain screen system. Cladding panels can be used to protect the load-bearing external walls from rain water, especially masonry and concrete. PV panels can be performed the function of such cladding and tiles. These structures are usually vertical. That ventilated cavity between the exterior cladding and the main wall help keep down the operating temperatures of PV cells, enhancing their performance and provide space for cables. PV screens have moderate power output due to vertical orientation. The stick system curtains wall and also the unitized curtain walls. So the stick systems curtain walls are used in those buildings that have internal columns or structural steel to support the main loads. Curtain walls are not weight-bearing, and their main function is to resist air and moisture infiltration. Also, building insulation is often attached to them. Warm facade. A popular solution is to build the curtain walls from aluminum and steel framing filled with glass panels. PV panels can be sealed into curtain wall structures in both vision area or opaque area of the facade instead of regular glass. The unitized curtain walls the unitized wall segments are pre-assembled at a factory and then are delivered to the building site. The controlled industrial environment provides more precision and equality of sealing the PV panels into the wall framework and making cable connections. Double skin facades. Glass facades are often designed as double skin when there is significant air space between the internal and external glass walls. This helps to reduce the heat transfer losses through the walls. PV modules can be readily integrated into the external facade. Ventilation through the double skin structure provides valuable cooling on the back of the panels. The atria and the canopies. For the highest performance, PV are best integrated into horizontal or tilted elements such as atria and canopies. These structures are usually free from overshadowing and are easy to ventilate. The solar thermal electric power generation. Solar thermal technologies are designed to convert the incident solar radiation into usable heat. The process of solar heat conversion implies using energy collectors, especially designed mirrors, lenses, heat exchangers, which would concentrate the radiant energy from the sun and transfer it to a carrier fluid. The fluid passes through the sunlight collector and becomes very hot. Typically, heat carrier fluids are water or steam, oil or molten salt. Then the fluid is transferred to the heat engine, which converts the energy electricity. So, as we can see in the figure, solar radiation, from solar radiation to black observer plate, and then transparent screens, from solar radiation, transparent screens, and then to black observer plate, and then the fluid tubes. So also the thermal insulation. So plate, uh, flat plate collectors. Flat plate collector is the simplest technology of this kind, which is typically used for reaching temperatures usually no more than 100 degrees above ambient. Concentrating collectors. The above collectors are combined to a bigger energy conversion system. The larger scale solar systems, I mean, the larger scale solar thermal systems have higher efficiency than small systems. The utility scale solar thermal systems include the following designs: the linear reflector, heating temperatures 280 degrees Celsius, the parabolic through heating temperatures 400 degrees Celsius. These are engine systems heating temperatures 650 degrees Celsius. A solar tower heating temperature up to or lesser than 1000 degrees Celsius. Utility scale geothermal energy system. There is a vast amount of heat contained by the Earth's interior. This internal heat is mainly comprised of the residual heat of planetary accretion and radioactive heat from radioactive element decay. The hottest part of the Earth is the core, a big part of which is the molten state. Heat radiates and gets transferred them from the core to the outer layers of the planet by interior fluids and melts. The temperature change rate with depth depends on the density and the thermal conductivity of the rocks. Subdivisions of the Earth's structure into layers is made according to the rock composition and geological properties. So we see that thermal profile within each layer can be quite different. The drastic change in temperature patterns around the boundary between the lower mantle and the outer core is apparently related to the transition of the molten state. So as what we can see in the figure, we have the temperature and the depth. So the lower the depth is, it can mas taas ang temperature, di ba? From lower mantle to outer core and to the inner core.
Wind energy applications and technologies. Wind energy is primarily used for power generation. Wind power conversion systems have been increasingly employed in the US, Europe, India, and more sparingly in some other locations over the last decade. Due to the development of technology that allows relatively high efficiency of wind resource conversion, we have here a video on how wind energy or the wind turbine works. Please watch this.
We've all seen those creaky old windmills on farms, and although they may seem about as low-tech as you can get, those old windmills are the predecessors for new modern wind turbines that generate electricity. The same wind that used to pump water for cattle is now turning giant wind turbines to power cities and homes. Okay, have a look at this wind farm in the California desert. A hot desert next to tall mountains, an ideal place for a lot of wind. Here's another one on the windy prairies of Wyoming. Now, today's wind turbines are much more complicated machines than the old prairie windmills, but the principle is the same. Both capture the wind's energy. Okay, here's how it works. First, a wind turbine blade works sort of like an airplane wing. Blowing air passes around both sides of the blade. The shape of the blade causes the air pressure to be uneven, higher on one side of the blade and lower on the other. And that's what makes it spin. The uneven pressure causes the blades to spin around the center of the turbine. On the top, there's a weather vane that's connected to a computer to keep the turbine turned into the wind so it captures the most energy. Now the blades are attached to a shaft which only turns about 18 revolutions a minute, and that's not nearly fast enough to generate electricity by itself. So the rotor shaft spins a series of gears that increase the rotation up to about 1800 revolutions per minute. And at that speed, the generator can produce a lot of electricity. So why are wind turbines so tall? Well, the higher up you go, the windier it is. More wind naturally means more electricity. And in many cases, larger turbines can also capture wind energy more efficiently. The blades can sweep a circle in the sky as long as a football field. Now, what's really cool is that even a small wind farm, like this one in Wyoming, can generate enough electricity to power more than 9,000 homes. And larger farms can provide much more clean energy for our homes and businesses.
Energy Return on Investment, or EROI. EROI is a common metric applied to the energy conversion systems. It is defined as the ratio of the lifetime usable energy generated by the system to the energy spent for the system manufacturing, operation, maintenance, and disposal. Obviously, EROI equals 1 would mean that over its lifetime, a system produces as much energy as is being consumed for its creation and operation. For wind turbines, the typical estimate of the error is in the range from 5 to 35, depending on the type of system. This indicator significantly increases the size of the turbine motor or rotor. The latest generation large-scale turbines yield EROI values about 35 and higher. Status of technology. The wind power generation systems have been commercialized for several decades now. The efficiency and durability of the systems was improved over time.
So, recent developments explain the growing interest in the wind energy and observed growth of wind energy market. Economic aspects. Economic analysis of renewable energy system mainly focuses on the ability of the system to pay back the initial investment and operation cost within a reasonable period of time. The biomass fueled combined heat and power system. Biomass as a source of fuel has been part of global energy economy throughout the human history. Using biomass as fuel via combustion may help solve the fuel supply issue, since biomass is renewable but does not help solve the global carbon emission and pollution problem. Burning biomass produces CO, CO2, and NOx, and other gases at levels exceeding those from traditional fossil fuels. The biomass combined heat and power CHP. Biomass-fueled CHP or generation is one of the applied technologies developed as cost-effective method of energy recovery. Because the byproduct heat generated in electricity generation is not wasted, but rather utilized as thermal energy. The total efficiency of such systems reaches from 60 to 80%. Excuse me. There are three main stages in the biomass fueled CHP process. First is the biomass collection and preparation. Secondly, biomass conversion from A to steam or B to biogas. Third, power and heat generation. The energy management and power systems. Base load power sources are the plants that operate continuously to meet the minimum level of the power demand 24/7. Base load plants are usually large scale and are key components of an efficient electric grid. Base load plants produce power and at a constant rate and are not designed to respond to peak demands or emergencies. The base load power generation can rely on both renewable or non-renewable resources. Non-renewable resources are such as fossil fuels, include coal, nuclear fuels. Renewable resources include hydropower, geothermal heat, biomass, biogas, and also a solar thermal resource with associated energy storage. There are the number of reasons why a plant can have lower than 100% capacity factor. Some of them are lower demand for electricity over certain period of time, under capacity operation due to maintenance, equipment failures or interruptions, resource fuel shortage, equipment upgrade or resulting in high nominal capacity. The base load power plants typically are uh, coal-fueled or nuclear plants due to low-cost fuel and steady-state power they can produce. Hydropower and geothermal power can also be used for base load electricity generation if those resources are regionally available. Apparently, the difficulty with renewables is their intermittence in time and location bias. Comparison of typical capacity factors of various energy systems reflects this difficulty. So there are comparison. First, the energy conversion system and the capacitor percent. The nuclear power, the coal, the natural gas, hydroelectric, concentrating solar, wind, and photovoltaic solar. So these are the capacity factors by percent. So the nuclear power has 90.3%, the coal has 63.8%, The natural gas has 42.5, hydroelectric 39.8, the concentrating solar 33, the wind 24.40, the photovoltaic solar has 15 to 19%. Capacity factors of power plant based on different fuel resources. Alternative fuel vehicle technologies. While the demand for transportation fuels is increasing, the continuing dependency of the U.S. economy of the foreign oil has put the country in extremely vulnerable position with respect to its meeting its transportation energy needs. This vulnerability is the critical motivator in searching for alternative fuels for vehicles and looking for alternative types of transportation as well. Sustainability of transportation basically means the flexibility and ability to provide for your own needs using the resources that are local, widely available, or renewable. A number of alternatives including both liquid and gaseous transportation fuels have been a subject of research and implementation for the last few decades. Let us review the background behind those options. Alternative fuel supply chain distribution. Viability of certain types of transportation fuels is closely related to the processing, supply, and distribution infrastructure. This is especially critical in the US society and economy, which have heavily reliant on the usage of road vehicles for personal and industrial needs. Transportation emissions. Strong motivators for developing alternative vehicle technologies and fuels are growing emissions and alarming urban air pollution levels. According to US EPA in 2017, CO2 emissions from transportation sector surpassed the long-time leader, electric power sector, in the total national emissions budget. This change in leadership in part happened due to increasing addition of natural gas and renewable sources to the power generation mix while retiring older coal power plants in a number of states. Zero-emission vehicles. The concept of zero-emission vehicles is typically attributed to the transportation options that do not result in any harmful emissions during vehicle operation. Harmful emissions are defined as those known to have a negative impact on the environment or human health. Typically, examples of non-zero emission vehicles are electric or battery-powered cars, electric trains, hydrogen-fueled vehicles, and human or animal-powered transportation. Example, bicycles, velomobiles, carriages, and etc. The battery technology for electric vehicles is based on charge or discharge cycles, meaning that the battery is charged beforehand using an electric source and is discharged during vehicle operation. The hydrogen-fueled vehicles are typically based on fuel cell technology, which imply electrochemical conversion of the fuel energy into electricity as opposed to combustion. So this is the demo plug-in battery hybrid vehicle by the stationary charger. Fuel cell technology for cars. Fuel cell is similar to battery in the electrochemical principle of energy conversion, but different in operation design. Instead of storing the reagents and products of chemical reactions inside, like batteries do, fuel cells operate on continuous flows or outflows of reagent and products. The main components of the fuel cell include membrane electrode assembly, which consists of a proton exchange membrane and electrodes, anode and cathode. Attach the membrane
On each side, gas diffusion layers, bipolar plates, and supporting structure. The fuel electrodes contain dispersed catalyst particles, usually platinum, which are necessary to promote electrochemical reaction.
Fuel cell cars, which run on electricity produced from compressed hydrogen, emit zero harmful emissions and could be the future of motoring. They can be just as fast, practical, and can travel as far as a conventional petrol or diesel engine car, but their technology is very different, and importantly, the only thing that comes out of the exhaust is water vapor. Rather than having a petrol or diesel tank like a conventional car, the fuel cell car has a tank that stores compressed hydrogen as a gas. Hydrogen is used as an energy carrier so that the fuel cell car can produce its own electricity on board rather than storing it in batteries. This compressed hydrogen is expanded and then fed into the fuel cell stack. The fuel cell stack is like a tiny electric power station. Inside it, the hydrogen combines with oxygen from the air to generate electricity and water as a byproduct. Water vapor is the fuel cell car's only emission. The electricity created inside the fuel cell stack is used to power the electric motor, which is in turn used to drive the car. The fuel cell stack is made up of hundreds of individual cells stacked together like a loaf of bread. In fact, each cell is like a sandwich with a membrane electrode assembly, or MEA, between two separators, or bipolar plates. The MEA is made up of a proton exchange membrane, or PEM, which sits between hydrogen and oxygen electrode layers and gas diffusion layers. In each cell, hydrogen gas passes over the hydrogen electrode. Each hydrogen atom is converted into a hydrogen ion in a catalytic reaction, releasing an electron in the process. The hydrogen ions then pass through the electrolytic membrane, where they bond with oxygen ions straight from the atmosphere. The previously emitted electrons from the hydrogen molecules arrive at the oxygen electrode via an external circuit. The released electrons create a flow of direct electrical current in the external circuit, and water is generated at the oxygen electrode as a byproduct. This water is drained from the system and exits the car as water vapor via the exhaust. Because the electricity is generated from hydrogen and oxygen, no carbon dioxide or other pollutants are emitted from the car. It's the ultimate in clean performance. Honda's FCX Clarity is the world's first production fuel cell car and is already on sale in the US and Japan.
Sustainable community and mass transit technologies. Sustainable community is a term usually applied to a certain inhabited entity, a neighborhood, a town, or a city that economically, socially, and environmentally healthy and resilient. The typical feature of a sustainably developing community is a holistic approach to meeting the local society needs, as opposed to the fragmented efforts which focus on one specific need and ignore others. The sustainability of the current communities that are heavily reliant on a car transportation becomes questionable for at least two reasons. First is the environmental impact. The greenhouse gas emissions, air pollution, depletion of petroleum resource, increased land and water use demands, and social impact. Overdependence on cars for basic needs and commuting, limited infrastructure to support growing car culture, decreased quality, and aesthetics of urban. Thank you for being with us from slide 1 down to slide 70. God bless you.
Good morning, everyone. My name is Nelson Naradaza, and I'm here to report to you about characteristics of artificial lighting. Okay, so this is all the outline of my report. Lamps, luminaires, and light fixtures. Light output, luminous efficacy, correlated color temperature, color rendering index, spectral power distribution data, lamp life, and depreciation of lamp output. So first is lamps, luminaires, and light fixtures. So lamps is a device that generates light, although frequently called a light bulb by the layperson. The term lamp rather than bulb is used in the lighting industry to avoid confusion when describing a light source, simply because a bulb is the glass portion of a lamp that encloses and protects the working parts of the light source, whereas a lamp is a source of light. Lamps fit into two broad categories. First is incandescent lamp. Incandescent lamp or incandescent light globe is an electric light which produces light with a filament wire heated to a high temperature by an electric current passing through it until it glows. The hot filament is protected from oxidation with a glass or quartz bulb that is filled with inert gas or evacuated. The light bulb is supplied with electrical current by feed through terminals or wires embedded in the glass. Most bulbs are used in the socket which provides mechanical support and electrical connections and has the capacity of 700 to 1000 hours and the temperature reaches about 2200 Celsius. Okay, second is gaseous discharge lamps. Gaseous discharge lamps can be further divided into two subcategories. First is low pressure lamps. A low pressure sodium lamp is a type of a lamp that produces light from sodium gas contained in the bulb, operating at a partial pressure of 0.13 to 1.3 Pascal. Low pressure sodium lamps are highly efficient electrical light sources. They emit a very yellow light and require a ballast like fluorescent bulb. Low pressure sodium lamps are require up to 10 minutes to start and have to cool before they can restart. Therefore, they are most suitable for application where they stay on for hours at a time. Most LVS lamps are used for driveways, parking lots, and pathways. The second subcategory for gaseous discharge lamps is high pressure or HID lamps. High pressure sodium lamps, also known as HPS lamps or HPS lights, are a type of sodium lamp that is widely used in industrial lighting in many public outdoor areas. They are commonly used in public parking lots, roadways, and other security areas. High pressure or HID lamps include mercury vapor, metal halide, and high pressure sodium lamps. It produces a dark pink glow when first struck, and an intense pinkish orange light when warm. Low pressure sodium light produce the greatest amount of light per watt of energy consumed. High pressure lights are slightly less efficient. The efficacy in lumens per watt for low pressure sodium lights is 60 to 150. For high pressure lights, it is 50 to 140. Luminaires and light fixtures. Lighting fixtures, also called as luminaires, helps to create artificial light with the help of lamp. Some luminaires also have switch to control the intensity of the light. Light fixture is a device that projects, diffuses, and alters the light direction of a given light source. Luminaires can also be referred to as system, as it contains the light source, the housing, the electrical system, the main connectors, reflectors, and shielding devices, or louvers. Luminaires are categorized by two major classifications of prime usage: indoor or outdoor applications. So for indoor, we have commercial and industrial, and for outdoor, we have public and amenity. Here are some examples for indoor commercial lightings for the office lighting fixture and for the retail lighting fixture. And here are some examples for indoor industrial lightings for manufacturing and cold storage light fixture. And for outdoor, public, and amenity lightings, here are some examples for parking and sports light fixtures. And for the street light, roads, and tunnels. Light output. Luminous flux. Luminous flux or luminous power is the measure of the perceived power of light. It differs from radiant flux, the measure of the total power of electromagnetic radiation, and that luminous flux is adjusted to reflect the varying sensitivity of the human eye to different wavelengths of light. The luminous flux is measured in lumen, simply Lm. A lumen is defined as the quantity of light given out through a steradian by a source of 1 candela of intensity radiating equally in all directions. 1 lumen is luminous flux, or expressed more simply, the total amount of light energy emitted into one solid angle, 4 pi or steradian by a point source having a luminous intensity of 1 candela. Its flux is equals to 4 pi. The steradian, or simply SR, is the SI unit of solid angular measure, where there are 4 pi or about 12.5664 steradians in a complete sphere, about 7.96% of the area of the sphere. Luminous intensity. A candela, or simply CD, is the SI unit of luminous intensity, that is the power emitted by a light source in a particular direction. 1 candela is 1 lumen per steradian. The candela is sometimes improperly called candle power, which was formerly defined as the light emitted from a wax candle. A lumen is roughly equal to the amount of candlelight striking a curved 1.0 or 1 surface that all points is held 1 feet or 1 meter away from the flame of a single candle emitting 1 candela of illumination. Luminous efficacy. Luminous efficacy is the ratio of the light output of a light source, a specific lamp, to the electrical energy consumed, including the ballast if applicable, to produce that light source. It is expressed in units of lumen per watt of electric power, and is thus typically referred to as LPW. LPW is equals to light output or lumen over power input or watt. To apply this formula, so let's have an example. Determine the luminous efficacy of the following lamps. First is a 40 watt incandescent lamp that emits 505 lumen of light. So naatay given nga light output, which is 505 lumen, over the power input, which is 40 watt. So we get 12.6 lumen per watt. For the second example is a 40 watt fluorescent lamp and a 4 watt ballast that emits 3050 lumen of light. So natay given nga light output, which is 3050 lumen over power input, which is 40 watt and a 4 watt ballast. Gi-add lang natin siya, so naman siyang 44 watt, and we get 69.3 lumen per watt. Correlated color temperature, or CCT. CCT is defined as the absolute temperature expressed in degrees Kelvin but theoretical black body whose chromaticity most nearly resembles that of its light source. CCT rating is an indication of how warm or cool the light source is. Ambient color and CCT of light have a psychological effect over the user. A color temperature less than about 3500 Kelvin provides warm lighting by emitting mostly yellow and red wavelengths. A color temperature greater than about 5000 Kelvin provides cool lighting because it emits light predominantly in the white and blue wavelengths. Neutral daylighting occurs when the color temperature of the lamp is between temperatures of 4500 and 6500 Kelvin, with the lower side of the range warmer and the upper side cooler. By comparison, a candle flame is about 1800 Kelvin and noon sunlight is about 5500 Kelvin. A warm light is produced by a light source that has a lower temperature. Typical color temperatures for commercially available lights are 2800 Kelvin incandescent and 3000 Kelvin halogen, 4100 Kelvin cool white fluorescent, and 5000 Kelvin daylight simulating fluorescent. Color Rendering Index. The Color Rendering Index, simply CRI, is a method of numerically comparing the color distribution of a light source to a reference lamp. A scale from 0 to 100% indicating how accurate a given light source is at rendering color when compared to a reference light source. The higher the CRI, the better the color rendering ability. Spectral power distribution data. A spectral power distribution curve is a graphic presentation of the quantities of light emitted by a lamp by wavelength component. These curves are a plot of radiant power versus a specific wavelength across the light spectrum. They provide a visual fingerprint of the color characteristics of the light emitted by the source over the visible part of the spectrum. A spectral power distribution curve of an ordinary household incandescent lamp will typically show a large increase in radiant power from 380 nanometer to 780 nanometer. Light emitted by the source is weak in violet wavelengths, 380 to 400 nanometer. It, in- it increased through blue, green, yellow, and orange wavelengths and very strong in red wavelengths, 600 to 750 nanometer. This type of lamp illuminates yellow, orange, and red colored objects very well. Depreciation of lamp output is a factor used by lighting designers to predict the depreciation in light output for a specific light source over a defined period of time. Defining the specific lamp lumen depreciation depends on the type of light source, such as metal halide, fluorescent, or LED. Lumen depreciation. Lumen output depreciates over time. Lumen depreciation will also be affected by dirt and dust in the environment. Lamps in soiled or dusty industrial and outdoor environments will become covered with dust or a soiled coating, so lamp output will depreciate. Lamp life. The rated life of a lamp is its median life expectancy, expressed in hours. It is the cumulative time that lapses before 50% of representative group of lamps has failed and the other lamps in the group continue operating. In other cases, rated life is difficult to determine because these lamps type will continue to emit light but get dimmer and dimmer with time. That is, they do not burn out. Lamp life generally decreases each time a lamp is switched on and off. A continuously lit lamp will normally last much longer than one that is switched on and off regularly because of energy cost. This reduction in life does not warrant leaving lights on in an unoccupied space. Life of an incandescent lamps will be affected by the voltage they operate at versus the voltage for which they were designed. A slightly lower voltage means increased life because of cooler operation, but this reduces light output. Life of fluorescent and HID is greatly affected by type of ballast. Lamp and ballast must be matched to ensure proper operation. For example, 20.2, a lamp manufacturer's specifications for a 40-watt fluorescent lamp indicates an output of 2,680 lumen, a rated life of 20,000 hours, and a cost of $6 per lamp. Data for a 150-watt incandescent lamp indicates an output of 2,850 lumen, a rated life of 750 hours, and a cost of $2 per lamp. When in use, it is anticipated that these lamps will be operated 10 hours per day and 220 days per year. Letter A. For each lamp, approximate the time period that elapses before replacement is necessary. For 150-watt incandescent lamp, we have the given value of 750 hours over 220 days per year times 10 hours per day. We get 0.34 years times 12 para makuha nimo ang 4.1 months. And for 40-watt fluorescent lamp, we have the given value of 20,000 hours over 220 days per year times 10 hours per day. We get 9.1 years or 110 months. And for letter B, approximate the cost of each type of lamp over a 10-year period, assuming use and lamp costs remain constant. And for 150 incandescent lamp, 10 years over 0.34 years per lamp, we get 29.4 lamps. 29.4 lamps over 10 years. So, every incandescent lamp mag-cost siya $2. So, we get $58.80. And for 40-watt fluorescent lamp, 10 years over 9.1 years per lamp is equals to 1.1 lamp. 1.1 lamps over 10 years at $6 per lamp is equals to $6.60.
My name is Kechi Esperona, and my topic for today is about light and architectural lighting system. My topic outline for today is incandescent lamps, tungsten halogen lamps, luminous efficacy, gaseous discharge lamp, fluorescent luminary efficacy, high-intensity discharge lamp, blended lamps, solid-state lighting, and mercury content of lamps. The first decision in the design of a good lighting system is the choice of light source. There are three groups by the construction and operating characteristics: the incandescent, the fluorescent, and the HID. The HID lamps can be grouped into four major classes: the high-pressure sodium, the metal halide, mercury, and the low-pressure sodium. First is incandescent lamps. What is incandescent lamps? These lamps produce visible light by heating a tiny coil or filament of tungsten, where that glows when it is heated by an electrical current. These are the familiar source of light, so-called the light bulb. Its advantages are low lamp cost, reliability, familiarity, and a good color condition. But they have a short related life and a poor efficacy, or the LPW, or lumen per watt. Lumen per watt is a key measure of efficacy in lighting. These incandescent lamps can be found in application needing excellent color condition, such as retail, furniture, clothing and grocery stores, hair and beauty salons, restaurant, and art studio. The basic design of the incandescent lamp has essentially remained unchanged since Thomas Edison introduced a commercial successful lamp in the late 1890s. Thomas Edison, or Thomas Alva Edison, was an American inventor and businessman who has been described as America's greatest inventor. He developed many devices in fields such as electric power generation, mass communication, sound recording, and motion pictures. When electricity flows through the filament of an incandescent lamp, the filament produces resistance against electrical current flow, causing it to heat up and incandescence, or glow with heat. Where the incandescent word came from. On the table 20.5, or lamp designation of selected bulbs, lamp designation description of bulb shape. First is lamp A, or the standard light bulb shape that can be found in the third to fifth bulb in the second row. Next is the ER, or ellipsoidal reflector, that can be found on the third bulb on the last row. Next is the IR, or the infrared reflecting. Next is MR, or multi-phase reflector. Next is the PAR, or PAR, or the parabolic aluminized reflector, that can be found on the last two bulbs on the last row. Next is the PS, or the pear-shaped bulb, that can be found on the last bulb on the second row. Next is the R, or reflector, that can be found on the first two bulbs on the second row. And lastly, lamp T, or the slender or tube-shaped bulb. This bulb can be found on the upper row and the first two tube bulb in the last row. Incandescent lamps have wattages of between 3 to 1000 watts and voltages of 6 to 277 volts. The 120, 125, and 130 volts lamps are the most common. Lamps are also designated with a number digit that indicates tube diameter in eighths of an inch. An R30 is an internal reflector lamp that is 30 eighths, or 3 3/4 inches in diameter, whereas an A19 is an ordinary pear-shaped lamp that is 19 eighths of an inch, or 2 3/8 inches in diameter, as shown on the picture. The medium base is a familiar threaded base found with ordinary lamps up to 300 watts. The candelabra base is the smaller threaded base used in ornamental lighting such as chandeliers. And it is also known as the candle or the torpedo bulb because of its shape. And the magle base is a larger threaded base found on lamps that are 300 watts or greater. Example is the frosted Mongol base. It has a 300 watts. In applications where lamps are broken fairly often, there are special plastic-coated lamps available. These lamps are not unbreakable, but they break less frequently. And when they break, the shattered glass is contained within the plastic coating. Example is the A60. This clear and tough plastic coating has excellent long-term resistance to extreme heat or cold. Next is the tungsten halogen lamps. Tungsten halogen lamps are frequently called the halogen lamps, are a smaller, brighter, and more expensive version of the incandescent lamp. These lamps contain high-pressure halogen gases such as iodine or bromine, which allow the tungsten filaments to be operated at higher temperatures and higher efficacies. A higher temperature chemical reaction involving tungsten and the halogen gas recycles evaporated particles of tungsten back onto the filament surface. This offers the advantages of better color condition, more light output, and a longer life. The tungsten halogen lamp cannot be touched by hand without depositing residual skin oils that substantially reduces the life of the quartz glass bulb. The same as the incandescent lamp, tungsten halogen lamps also has the lamp designation, the TB, PAR, MR, T, and R. Tungsten halogen lamps has 6 components: the contact, base, capsule support, halogen filled capsule, tungsten filament, and the bulb. The tungsten filament of a halogen lamp has 2 purposes. One is to generate light, and the second is to generate the heat necessary to obtain a wall temperature exceeding to 250 degrees Celsius. These lamps have been designed to maintain this required wall temperature when operated at designed voltage. Next is the gaseous discharge lamps. A gaseous discharge is electricity passing through a gas such that it causes the gas to arc. A gaseous discharge lamp produces continuous light by passing electricity through a gas contained within the lamp. This electric discharge generates light directly or by producing ultraviolet radiation that causes a phosphor coating on the inside of the lamp to glow. Unlike incandescent lamps that produce light by getting a filament hot, while on the other hand, light is produced by a continuous gaseous discharge. All gaseous discharge lamps require an additional device called a ballast. A ballast is a voltage transformer and current limiting device designed to start and properly control the flow of power to discharge light sources such as fluorescent and HID lamps. It does not produce light directly. Instead, it is needed to create the starting voltage kick that causes the gas to arc and then controls the electrical or the voltage, the current, and the waveform input to the lamp that is necessary for proper operation. There are many types of ballasts. Magnetic or iron ballasts increase and control voltage. They are heavy and make noise hum. Electronic ballasts use solid-state electronic components. They tend to operate more efficiently with less noise and are capable of dimming lamp or lumen output. A is extremely quiet, like libraries or churches. B is slightly noisy, like classroom, seminar, or offices. And C is the moderately noisy, like workshop or open forum. Next is fluorescent lamps. A fluorescent lamp is composed of a tubular glass bulb that is covered with a thin phosphor coating on its inside surface. The glass bulb is filled with low-pressure gas containing mercury vapor. The base or bases at the end of the lamp are designed to connect the lamp to an electrical circuit. Fluorescent lamps use 25 to 35% of the energy used by incandescent lamps to provide the same amount of illumination, or the lamp efficacy of 30 to 110 lumens per watt. They also last about 10 times longer, 7,000 to 24,000 hours. Cathodes are filament-like coils at the end of the bulb that act as terminals of the electric arc. When energized, ultraviolet radiation from the mercury arc causes the phosphor coating to fluorescent. That is, they emit visible light as a result of being irradiated by electromagnetic radiation. Fluorescent lamps has 6 components: the AC main, switch, bipin, bimetallic contacts, cathode, and lastly the ballast. So there are types of fluorescent lamps. Linear fluorescent lamps, or the LFL, are commercially available in straight U-shape of circular tube in a variety of sizes, wattages, voltages, colors, and types of bases. A code composed of several digits is used to identify a specific lamp. For example, the standard lamp for general classroom and office lighting for several decades has been the F40 T12ES. The digit F is for fluorescent. The digit 40 indicate the nominal wattage. The digit T is for a tubular shape, or U for U shape, and C for circular shape. The digit 12 indicates tube diameter in eighths of an inch. And ES stands for energy saving. Compact fluorescent lamps, or the CFL, are miniatured fluorescent lamps. Traditionally, CFLs are manufactured with an integral ballast and a standard screw base that can be installed in standard light fixtures in place of incandescent lamps. CFLs combine the energy efficiency of fluorescent lighting with the convenience and popularity of incandescent fixtures. CFLs fits most fixtures designed for incandescent bulbs and use about 75% less energy, although CFL costs a bit more than comparable incandescent bulbs. They last 6 to 15 times as long, or 6,000 to 15,000 hours. These are designed as a substitute for standard size incandescent lamps. The 7 watts CFLs replace 25 watts incandescent lamps. The 11 watts CFLs replace 40 watts incandescent lamps. The 13 watt CFLs replace 60 watts incandescent lamps. The 19 watts CFLs replace 75 watts incandescent lamps. And 23 watts of CFLs replace 100 watts incandescent lamps. The 120 volts lamps are the most common used fluorescent lighting in residential and light commercial applications. Structures that have 277 or 480 volts, 3-phase power available, such as retail shopping malls, schools, hospitals, groceries, supermarket, and office buildings, typically use the 277 volts component of this system for the fluorescent lighting, where fixtures are not located closer than 3 feet away from windows, platforms, and fire escapes. Fluorescent lamps come in a variety of colors or temperature, such as daylight, cool white, soft white, warm white, and deluxe warm white, that covers the color temperature range from 3000 to 6500 Kelvin. Color temperature varies with the type of phosphor coating. The phosphor blend in a fluorescent lamp determines the color temperature and the color rendering of the light emitted by the lamp. Fluorescent luminaire efficacy. The luminaire efficacy rating, or the LER, is the ratio of light, the luminous flux in lumens, emitted by a fluorescent luminaire to the electrical energy consumed, including the ballast. The LER is found by the following equation, where the luminaire efficiency, or EFF, luminaire power input, or the watts, the ballast factor, or the BF, are from the fixture manufacturer's data, and the total rated lamp lumens, or the TLL. Luminaire efficacy rating is equals to the luminaire efficiency times the rated lamp lumens times the ballast factor divided by the watts. In example 20.3, fixture manufacturer's data for a 2-lamp fluorescent luminaire provides a luminaire efficacy of 0.60, a luminaire power input of 85 watts, a ballast factor of 0.87. Data from the lamp manufacturer indicates that the fluorescent lamps under consideration will output 3050 lumens. Compute the LER. LER is equals to EFF, which is 0.6, times the TLL, which is 3050 lumens, times 2 because of 2 lamp fluorescent, times the BF, which is 0.87, divided by 85 watts, is equals to 37.5 lumens per watt. Next is the high-intensity discharge lamps. High-intensity discharge, or the HID lamps, produce a very light by discharging an arc when electrical current passes through a metal gas contained under high pressure in a glass bulb. HID lamps include mercury vapor, metal halide, and high-pressure sodium lamps. These lamps differ from fluorescent lamps in that their gas is under higher pressure, the lamp is physically smaller, and the emitted light is more concentrated. HID lamps have an internal arc tube that contains the fuel gas. A large outer glass bulb surrounds the arc tube to avoid shattering that can result from direct contact with water and other fluids. The following is a description of the common types of HID lamps. First is the mercury vapor or MV. Lamps were the first commercially available HID lamps. These lamps are constructed of an internal quartz tube enclosed in an outer glass envelope. A small amount of liquid mercury is sealed in an argon gas field inside the quartz tube. After the warm-up period, the arc emits both visible and ultraviolet light. Phosphor coating can be added to improve color condition. MV lamps are available in wattages ranging from 50 to 1000 watts. Commonly seen on a street lights as shown on the picture. The mercury vapor lamp is a high-intensity discharge lamp. It uses an arc through vaporized mercury in a high-pressure tube to create a very light directly from its own arc. This is different from fluorescent, which use the mercury vapor arc to create a weaker light that mainly creates UV light to excite the phosphor. The merc, as it's known, has been a workhorse for society. Light street, factories, and large areas for over 100 years. Metal halide or the MH. Metal halide lamps are constructed in a manner similar to the MV lamps, except that in addition to the mercury and argon, various metal halides are included in the gas field. Use of metal halides increases luminous efficiency and improves color rendition. They are available in wattages ranging from 32 to 1000 watts. The small 32 watts MH lamp produces 2500 lumens, about as much light as a 150 watts incandescent or a 40 watts or 4 feet fluorescent lamps. High pressure sodium or the HPS. High pressure sodium lamps contain an internal arc tube made of a translucent ceramic material rather than quartz glass because of the high temperature ranging from 2350 degrees Fahrenheit or 1300 degrees Celsius at which it operates. The arc tube is enclosed in a outer glass envelope like other HID lamps. A small amount of solid metallic sodium and mercury is sealed in a xenon glass field inside the ceramic arc tube. HPS lamps are available in wattages ranging from 18 to 1000 watts and vary more widely than other HID lamps in their efficacy and color quality. Also can be found on the street lights. Low quality outdoor HPS lamps produce an orange-white light. And lastly, the low pressure sodium or the LPS. Low pressure sodium lamps are really a blend between HID and fluorescent technologies. These lamps are constructed of a large sodium-resistant glass tube containing sodium and a neon argon gas mixture. Colors are dramatically changed. Most red appears bright orange and green and blues appear dark. As seen on the picture, the color is originally red but it appears as a bright orange. Blended lamps. Blended lamps combine the luminous efficiency of an HID lamp like MV with the good color rendering capability of an incandescent lamp. The most common blended lamp has mercury vapor combined with a tungsten filament. The tungsten filament acts as an incandescent lamp, so a blended lamp requires no external ballast or other control devices. A key advantage of mercury tungsten blended lamps is that they are directly interchangeable with incandescent lamps and have a longer lamp life. A disadvantage is that they cannot be dimmed. Solid-state lighting. Solid-state lighting, or the SSL, refers to a type of lighting that uses light-emitting diodes or the LEDs, organic light-emitting diode lights or the OLED, or polymer light-emitting diodes or the PLED, instead of traditional lighting sources that use an electrical filament or gas inside a glass bulb. A light-emitting diode or the LED is a semiconductor that consists of a chip of semiconducting material treated to create a structure with two electron-charged materials. OLEDs, or the organic light-emitting diode lights. As seen in the picture, it is used especially on cars or motors, but mostly nowadays they use LEDs on their motors because it is much cheaper than the OLEDs. When connected to a power source, electrons jump from one material to the other. As an electron jumps, it emits energy in the form of a photon or light. The color of light created depends on the amount of energy in that photon, which depend on the material used for the layers. A single LED is about the size of a pea. It is powered by about 1 watt. LEDs are vibration and shock resistant. They have no moving parts, no fragile glass, no mercury, no toxic gases, and no filament. They are not subject to sudden failure or burnout and have an exceptional long life with a range of 50,000 to 100,000 hours. Lastly is the mercury content of lamps. Fluorescent and HID lamps have some mercury content and may need to be recycled or disposed of in hazardous waste landfills instead of municipal solid waste landfills under the U.S. Resource Conservation and Recovery Act. In recent years, the major lamp manufacturers have introduced a number of low mercury fluorescent and HID lamps, allowing them to be disposed of in municipal solid waste landfills. In anticipation of the global phase-out in 2020 of specific mercury-added products, including certain types of fluorescent lamps, the Eco Waste Coalition pressed for essential labeling information to assist consumers in picking fluorescent bulb with the lowest mercury content. In fluorescent linear tubes, it has 5 to 15 milligrams of mercury. It depends on various factors, type, manufacturer, or when manufactured. Next is compact fluorescent lamps with 4 to 6 milligrams of mercury, and it also is an energy saver. Next is high intensity discharge or HID lamps, mercury vapor, and high pressure metal halide with 13 to 80 milligrams of mercury and 225 milligrams in sports stadium lamps. Also 10 to 170 milligrams of metal halide in metal halide lamps. Lastly, the high-pressure sodium lamps with 15 to 30 milligrams of mercury. But some of the high-pressure sodium lamps do not contain mercury. Our next topic is forms of architectural lighting. Our topic outline is ambient lighting, task or local lighting, decorative lighting, and lastly, the emergency and safety lighting. Forms of architectural lighting. Architectural lighting. Good architectural lighting is crucial to the performance of everyday activities and to the appreciation of the built environment. The basic functions that light performs in interior building spaces. Ambient lighting, sometimes called general lighting, provides uniform illumination throughout the space. It softens shadows on people's faces and provides the illumination for color and texture. Ambient lighting is the most essential form of lighting because it fills the volume of a room or space with uniform light. The amount and type of ambient lighting depends largely on the activities or tasks performed in the space and color of the walls, ceiling, and furniture, as we see on our modern houses. These are the examples of ambient lights for wall, furniture, and for ceiling. Task or local lighting is the illumination provided for a specific visual function, which is additional to and controlled separately from the ambient lighting. Task or local lighting can be used such as sewing, drafting, assembly, and surgery. Generally require this type of lighting. As seen on the example picture, it tells that this task or local lighting has one specific subject. Task lighting is especially useful for seeing small objects of low contrast. Accent lighting is a directional lighting used to emphasize a particular object or area. It is used to call attention to or orchestrate interest by emphasizing a particular architectural feature, piece of art, photography, or plant. We mostly see it on a museum or we're going on a gallery. It's important to do accent lighting right, which means doing it subtly. Make people notice the object you're lighting, not the way that it is being lit. Decorative lighting is the light source that adds a quality of interest to the space. It combines with other types of lighting to give an overall feel to a room that serves little purpose other than to look attractive. This type of lighting may be a hanging crystal chandelier used as a main feature in an entry or a dining space. It is like a jewelry for the home. It helps your space sparkle and shine. Its role being mainly aesthetic. It can be used as mood lighting and can take many different forms, depending the style, the space, and its function, and lots of other details. Emergency and safety lighting. Emergency and safety lighting is a secondary lighting system that provides backup illumination when the power supply to the normal lighting system is interrupted or failed, such as in the case of a public utility power outage. Emergency lighting is required in the critical care and emergency spaces found in hospital, nursing home, and police, fire protection, mall, and crisis management areas. It is also refers to battery back or otherwise independently powered light sources that are designed to activate when a power outage creates low visibility condition in a workplace. Standby lighting is part of the emergency lighting system. It enables normal activities to continue substantially unchanged. This type of lighting system is typically powered by an emergency generator or battery backup system. This system must meet stringent regulation and be tested frequently to ensure proper operation during a power interruption. And lastly, these three important emergency lighting that can be found anywhere, especially on a building. Safety lighting is the part of emergency lighting system that ensures the safety of people involved in a potentially hazardous process. Next is the escape lighting. Provides illumination to ensure that an escape route can be effectively identified and used in the case of failure of the normal lighting system. And lastly, exit lighting is the part of the escape lighting system that includes illuminated signage used to provide clear direction for an emergency exit of building occupants. Exit signage is typically required above exit doorways and in a corridor that serve as a means of safe exit from the building interior. Especially nowadays, this emergency and safety lighting can be found in every building structure. This emergency and safety lighting can help all of the occupants to escape or exit in a building in case of an emergency. That's all. Thank you. The next reporter is Jonathan Rimando.
Good morning, everyone. My name is Jonathan Adam Rimando, and for this presentation, I will be discussing three topics under light and architectural lighting system, which is lighting installation, light distribution and glare, and illuminance and luminance. Let's have first lighting installations, and under this, we have the traditional lighting installation. There are many types of luminaires and lighting installations that can illuminate a building space or highlight a centerpiece. Luminaires has three common types: the indoor, outdoor, and specialty. Indoor are luminaires that are found inside a structure. Outdoor are luminaires that are found outside a structure. And specialty are luminaires that are used in a program. We have seen example of luminaires. Pendant. A pendant is a luminaire that is hung with a cord, chain, or tube that enables it to be suspended from a ceiling or other supports. It broadcasts light over the entire space. Uplight. An uplight is a luminaire where a shielded light source directs its light to the ceiling, where it is reflected back to the space. It is also used for decorative. Downlight. A downlight is a luminaire that is usually attached to or recessed in the ceiling and emits a concentrated light downward. A hi-hat. A hi-hat is a type of downlight that is recessed canister-shaped luminaire with a shielded lamp that emits light downward. Resist. Resist is a luminaires are mounted above the ceiling or behind a wall or other surface so that any visible projection of light is insignificant. Sconces. Sconces are decorative wall-mounted luminaires that provide ambient illumination. They can direct light upward, downward, or in all directions. High bay. High bay luminaires are used in high ceiling areas 20 feet or 6 meters or higher that require uniform illumination. High bay fixtures installed in a grid pattern are typically used to provide ambient illumination in warehouses, gymnasiums, and retail superstores. These luminaires are high wattage with 200 watts or more, so they can deliver light over long distances. The fixture size is fairly large, about 2 feet or 0.6 meters for a typical fixtures. Low bay luminaires are more compact. They they are designed for use in low to medium ceiling areas, 12 to 20 feet or 3 to 6 meters. They are typically used for general illumination in office, retail spaces, and loading dock areas. Both high bay and low bay luminaires can be used in uplighting and downlighting application. Directional lighting is illumination where light received at the work plane or light illuminating an object and incident predominantly from a particular direction. The only light that is important is the light that falls where it is needed. Spot, flood, and track lighting are common types of directional lighting. A spotlight is a luminaire that is designed to emit an intense, concentrated beam of light with usually no more than a 20-degree divergence or spread from where it is directed. A floodlight is a luminaire that emits an intense light that is broader than a spotlight and that is capable of being pointed in any direction. Track lighting is a directional lighting installation where luminaires are attached to and are movable along a metal track. A more subtle method of directional lighting involves the use of one of the many different resist downlight. Diffused lighting. Diffuse lighting is a lighting installation in which the light on the plane or on an object is not incident predominantly from a particular direction. Diffuse light is cast and dispersed over a large area. A diffuser is a lighting component such as a translucent glass refractor that redirects or scatters the light from a source. This light of lighting This type of lighting can be produced by a variety of indirect lighting techniques, where much of the light reaches the work plane after it has reflected off another surface, such as a wall or ceiling. Diffuse lighting is frequently used to provide soft background lighting. Cornice, cove, and valence lighting fit in a category of indirect, diffused lighting installation called wall washer. Cornice lighting is a lighting installation where the light source is shielded by a panel that is parallel to the wall and attached to the ceiling. It, it distributes light over the wall. Cove lighting is an uplighting insulation where the light source is shielded by a ledge of recess with light dispersed over the ceiling and upper wall. Valence lighting is a lighting installation where the light source is shielded by a panel that is parallel to the wall at the top of a window. Fluorescent lighting is widely used for general lighting installation in buildings. Fluorescent luminaires are available in recessed, surface mounted, or pendant style fixtures designs. Unlike the concentrated light emitted by other commercially available light sources, fluorescent lamps produce a diffuse light that is relatively glare-free and visually comfortable. We have there also reflector lamps. Reflector lamps are incandescent compact fluorescent or HID lamps with a built-in reflecting surface. Incandescent and HID versions are made from a single piece of blow-molded soft or hard glass. Compact fluorescent version may be one piece or may be designed so that the inner lamp can be replaced. An elliptical reflector or ER lamp is an incandescent lamp with an elliptically shaped reflectors. This shape produces a focal point directly in front of the lamp that reduces light absorption in some types of luminaires. It is particularly effective at increasing efficiency of baffled downlight. A parabolic aluminized reflector or PAR lamp which may use an incandescent filament, a halogen filament tube or HID arc tube, is a precision pressed glass reflector lamp. PAR lamps rely on both the internal reflector and prisms in the lens for the control of the lighting beam. Remote source lighting or RSL is an advanced lighting technology that transports light from a single source over a distance to one more light outlets or emits light evenly along the way. It is typically more costly than traditional lighting installation, but can provide an aesthetic appeal that cannot be achieved by other means and therefore can be effective as accent or decorative lighting. Additionally, health and safety benefits resulting from the RSL delivery system includes a decrease in infrared and ultraviolet energy introduced into a space and improve safety in damp or exclusive environment. Losses in the light distribution system generally make RSL less energy efficient that co- that conventional systems. In many cases, precision targeting and light can make up for those losses. Remote source light is distributed using fiber optic or light pipes systems. Fiber optic RSL system. It consists of a light source, a set of reflectors, filters, and lenses to feed the light to the fiber optic cables, and a fixture to distribute the light at the point of illumination. The number of fixtures that can be fed from the light source depends on the intensity of the light source and the light requirements at the end of the run. For decorative application where light distribution is that crucial, several hundred fixtures might be fed from one source. Light pipe RSL systems is feature a hollow tube with a reflective inner surface and directs light through the tube. The most common linings are prismatic films and mirrored surfaces. Most light pipe applications required side emitting tubes that can carry artificial light or daylight. These feature a layer of translucent or transparent materials surrounding a layer of prismatic light reflective system. The light is released evenly along the length of the tube. Mirrored surface tubes are most often used with daylight pipes and emit light at the end of the tube. Let's proceed to light distribution and glare. Let's have first distribution of light. One of the primary functions of luminaire is to throw light only where it is needed. Light can be directed downward for maximum use or directed to the ceiling and upper walls and then reflected to all parts of the space. Table 20.15 shows the classification of light distribution produced by luminaires. It is helpful for a designer to know how a specific luminaire broadcasts light. A candle power or candela distribution curve is a graphical representation that illustrates the luminous intensity around the cross-section of a lamp or luminaire. It is a curve on a polar graph that shows the relative luminous intensity in candela around the lamp or luminaire. A candela power distribution curve can be thought of as a cross-sectional map of intensity or candelas measured at many different angles. It is a two-dimensional representation and therefore shows data for one place only. If the distribution of the unit is symmetric, the curve in one plane is sufficient for all calculation. If asymmetric, such as with street lighting and fluorescent units, three or more planes are required. In general, A single vertical plane of photometry describes incandescent and HID reflector units. Fluorescent luminaires require a maximum of one plane only along the lamp axis, one across the lamp axis, and one at 45-degree angle. Candle power or candela distribution curves of different types of downlighting luminaires are shown in figure 23.13 and 20.14. The heavy dark line is a curve that represents a specific luminous intensity at various positions beneath the luminaire opening. Figure 20.14 shows distribution curve for three different compact fluorescent luminaires. In this figure, it is evident that distribution is characteristic of a specific luminaire. A candle power distribution curve for a specific luminaire is available from the luminaire manufacturer. This information is useful to the designer because it shows how much light is emitted in each direction and the relative proportion of downlighting and uplighting. Second is glare. Glare is excessive brightness in the field of vision that causes discomfort or, in extreme cases, produces a disability from a temporary loss of vision. It is a visual sensation caused by luminance that is sufficiently greater than the luminance to which the eye are adapted. Glare can be an irritant of or impediment to vision. Glare can be caused directly from a bright light or from the reflection of light off a glossy surface. Discomfort glare cause visual discomfort without necessarily impairing vision. To prevent the design of lighting installation that produce discomfort, the visual comfort probability is calculated. The visual comfort probability, or VCP, is a rating of a lighting installation expressed as a percentage of individuals who, when viewing from a specific location and in a specified direction, will be expected to find it acceptable in terms of discomfort glare. In most cases, the VCP should exceed percent, that is at least 70% of a statistical group of individuals will rate glare levels acceptable in the space being illuminated. Disability glare occurs when visibility is impaired from excessive brightness. This type of glare can occur when light scatters in the eye in such a way as to put a veil of luminance across the retina. This type of glare is much like a temporary effect a close-up photographic flash has on the vision of the viewer. It should be avoided at all costs. Direct glare occurs when excessive light enters the eye directly from a light source. It can occur even if the eye is not looking directly at the source. Problems with direct glare arise from improper placement of the light source, an exposed bright light source, or a improperly installed or poorly designed light fixtures. Reflective glare is the result of the lighting entering the eye after reflecting off a glossy surface. This type of glare can occur if the light source is positioned in such a way that its reflective light creates a veil or luminance across the visual task. Third is glare control. Preventing glare requires special attention to fixtures design, selection, and position to prevent light from entering the glare zone. The glare zone is defined as a zone above a 45-degree angle from the fixture's vertical axis. When light is emitted into the glare zone, Direct glare and reflected glare are likely to light emitted in the glare zone can cause visual discomfort. Positioning and selecting light fixtures that do not throw light in the glare zone is a good way to reduce problems with glare. Lenses. Lenses are typically made from clear UV stabilized plastics. Clear lens types include prismatic, batwing, linear batwing, and polarized lenses. White translucent diffusers are much less efficient than clear lenses, and they result in relatively low visual comfort probability. Louvers. Louvers are slats in a light fixtures that create opening for emitting light. Louvers provide superior glare control and high visual comfort compared with lens diffuser system. The most common application of louvers is to eliminate the fixture glare reflected on computer screens. Buffles. Buffles are opaque or translucent elements that shield a light source from direct view. They are typically part of the light fixtures. In the cross-section of the light fixture shown in Figure 20.13, baffles prevent the light source from throwing the light beyond a 30-degree angle from the fixture's vertical axis. Baffles keep the light from being broadcast into the glare zone. Let's proceed to the last topic, which is illuminance and luminance. As described previously, illuminance is the amount of light incident in striking a surface. Luminance is the amount of light leaving an object, thus relating to how bright an object appears to the human eye. Although an object may be illuminated, the eye cannot see it without visible light leaving or reflecting off the object in the direction of the viewer. The luminance of the surface is equal to the reflected illuminance. What is luminance? Luminance is a luminous intensity of a surface in a given direction per unit of projected area of the surface. Luminance can be expressed in two ways, in candelas per unit area or in lumens per unit area. There are many different standard units of measurements. For example, candela per unit inch. Foot Lambert, or luminance of a surface emitting the lumen per square foot, and the Lambert, luminance of a surface emitting the lumen per square centimeter. The relationship behind these units of measurements are 1 candela per inch squared is equivalent to 452 foot Lambert, and 1 Lambert is equivalent to 929 foot Lambert, are equivalent to 2.054 candela per inch squared. It is not necessary to go beyond this brief definition because luminance is seldom used. What is illuminance? Illuminance it is the density of luminous flux striking a surface. It describes how bright a surface may appear to the human eye depending upon the surface's reflectance. The appropriate units of measurements for illuminance are foot candle and lux. The foot candle, or FC, is the unit of measure of illuminance E, the intensity of light falling on the surface. It is equal to 1 lumen of light uniformly illuminating a surface over the area of 1 square foot. 1 foot candle is equivalent to 1 lumen per foot squared. The foot candle, the oldest physical unit still in common use, was originally defined as the illuminance striking a surface held 1 foot away from a burning beast wax candle. Foot candles incidents on a surface are related to the lumens striking the surface and the area of the surface A in foot, foot squared. The SI metric unit for illuminance is the lux, which is 1 lumen of light uniformly illuminating a 1 square meter surface, lumen per meter squared. Lux incident on a surface are related to the lumens striking the surface and the area of the surface in meter squared. 1 foot candle is roughly equal to 10 lux. Foot candle or FC is equivalent to 10.764 lux, while lux is equivalent to 0.0929 foot candle. Typical values of illuminance for selected conditions are provided in Table 20.16. By comparison, natural sunlight illuminates a surface 100,000 times more than light cast by a full moon on clear night. Illuminance at a specific location in a room or space can be measured with a portable handheld photometer that is commonly called a light meter. The IESNA prescribes exact methods of determining illuminance in its lighting handbook. Light meter readings at a specific location are generally performed by holding and placing the meter in a horizontal position on a desk or tabletop in the location where the task will be performed. In special instances, such as warehouse, shelving and library book stacks, the meter is held vertically. Care must be exercised to ensure the shadows from the meter use do not improperly influence result. Average illuminance in a space can be determined by dividing the room into a grid pattern that does not correspond with the spacing of the light fixtures and averaging the readings. Because of site condition and manufacturing tolerances, average measured values may vary by 20% or more from calculated designed values. Recommended illuminance. Historically, the chief goal of architectural lighting was to introduce as much light as possible to a building interior. That is, more light was good. The result was large lighting installation that consumed a lot of energy. The illuminance categories are ranked in alphabetical order from A through I by type of activity and seeing difficulty as outlined in the following. Categories A through C have ranges of illuminance from 2, 3, 5 to 10, 15, 20 foot candle, 20, 30, 50 to 10 to 100, 150, and 200 lux. They are for ambient lighting in public and working spaces, including corridors, lobbies, stairs, and conversation areas. Example is restaurant and exhibition areas. Categories D through F have ranges of illuminance from 20, 30 to 50 to 100, 150, 200 foot candle, or 200, 300, 500 to 1000, 1500, 2000 lux. They are for common visual tasks requiring more difficulty such as in classroom, office, and drafting areas, laboratories, and kitchen areas. Categories G through I have ranges of illuminance from 200, 300, 500 to 1000 1,500, 2,500 foot candle, or 2,000, 3,000, 5,000, 10,000, 15,000, 20,000 lux. They are for prolonged, visually demanding tasks involving sewing, precision, ma- machining, and surgery. Recommendations for levels of lighting in various spaces are provided in Tables 20.17. In general, recommended lighting levels increase as the size and contrast of the visual task decrease. Thus, the recommended lighting level will be near the lower level of the range when the size and/or contrast of the visual task is large, and will be near the upper level of the range when the size and/or contrast of the visual task is small. Governmental entities may specify levels of illumination.